All right, guys. I welcome you to this week's interactive session on the course Viscous Fluid Flow. So, just one second. Yes. So we were discussing boundary layer theory, precisely the laminar boundary layer theory in the last class, and we specifically looked into certain examples involving the momentum integral approach, where we estimated the where we estimated certain forms of the velocity profile, keeping in mind that the boundary conditions are satisfied on the edge of the plate and at the surface of the plate, basically. So for instance, we looked into a problem where the velocity profile was a sinusoidal function of y by delta, and then we evaluated what would be the boundary layer thickness by following the momentum integral approach, and then evaluated the displacement thickness and the drag force on a plate of width d and length l. And we looked into something which is known as the coefficient of drag, uh, and then we evaluated the drag force basically. Thereafter, what we saw is a problem which involves the Blasius flat plate solution. So it involves a little bit of understanding of how the Blasius flat plate problem is being done. And there, what the question asked us was to evaluate the characteristic stream function, which eventually we need to use to solve the Blasius equation, because it was essentially a 2D problem that we are solving. So there, what we did is we started off with the momentum equation, which is the x direction momentum flat plate boundary layer equation. And then in order to find the characteristic stream function, we need to express the velocities u and v in terms of the stream function. And then what we did is we looked into the scaling analysis of the terms, let's say the x direction displacement, or the characteristic length in the x direction, the characteristic length in the y direction. And then what we did is we took a characteristic stream function psi c, then just by following the scaling analysis, that is by matching the order of magnitude of the terms on the left and the terms on the right, that is we balanced the inertia term with the viscous term, of course, and we found out that the stream function essentially scales as root over of u infinity L nu. And this is actually the basis on which the stream function is non-dimensionalized when we follow the Blasius flat plate solution. So this is something that we saw. Thereafter, we solved like a more realistic problem, which involves the flow of water over a smooth flat plate with some given velocity and given length of the plate, where we find out what would be the boundary layer thickness at a particular location on the plate, the rate at which delta change with respect to x, that is how d delta by dx change, and also we evaluated the drag coefficient, which in turn gave us the drag force. We ended our discussion with something which is known as flow separation, and we said we will discuss more on it, on how flow separation basically takes place on flows over wedges, which is essentially obtained from the Faulkner scan solution that you guys studied during the lecture videos. But we'll look something like something related to that, and we will hopefully it will also revise the concept that you guys studied in that week's lecture. But nevertheless, what this problem that we saw, it asks us that, so it was just an analysis of flow separation, which where we saw basically two statements. The first statement said that adverse pressure gradient is a sufficient condition for flow separation, while the other statement said that the necessary and sufficient condition for flow separation to take place is that the velocity profile must have an inflection point. So so these are the two statements that we saw basically, and then we did certain analysis, and then we saw that the later statement is essentially true. That is, the velocity profile must have an inflection point for flow separation to take place, and this is the sufficient condition. And we said that that the existence of an adverse pressure gradient is necessary, but it does not mean that whenever there is a pressure gradient, there will always be flow separation. So it's not a sufficient condition, but it's a necessary condition. So the sufficient condition was that the flow profile must have an inflection point. So I again repeat, the meaning of an inflection point is that the second derivative of velocity of the u direction velocity with respect to the cross gradient, that is y, is basically equal to 0. That's the meaning of flow separation. So we will we will finish boundary layer by discussing certain things that so there is a doubt in the last class, so as to like relate how does flow separate, so how flow separation is essentially related to the flows over wedge or flows over surfaces which are obviously now not flat in nature, because we saw that whenever there is a flat plate, the pressure gradient in the x direction essentially come out to be zero, which can be easily like shown by applying the Bernoulli's equation outside the viscous layer, and we eventually saw that dp by dx essentially came to be zero in case of a flat plate. However, if there is not a flat plate, for instance, there is a flow over a wedge, which which you can see of course here, and the wedge angle in radian is given by some beta times pi by 2, where you don't need to worry about this pi by 2 factor, it's just a scale factor basically. And this beta that you see here, this is basically the wedge angle in radian. And then what we seek to find out is this: just by changing the profile of this wedge, there can be a favorable pressure gradient and there can be adverse pressure gradient in the direction of flow. For instance, what I mean to say is that if I change the geometry of this wedge, then dp by dx would essentially change. This means it can be greater than 0, it can be less than 0, or it can be equal to 0 in the limiting case of a flat plate. So what I mean to say is that, so the bottom line of this analysis is that you can eventually show that the existence of an adverse pressure gradient or a favorable pressure gradient is manifested by this wedge angle. That is what you can infer from it. Okay, so we will shortly see wow, how does this happen. So for instance, you guys must have seen that now the far field flow which is basically u infinity. So now, yeah, so since you guys know the flow, so the far field flow will, if there wasn't a plate present, the far field flow would basically be parallel, or I mean that the streamlines would basically be parallel in this direction. Now since there is a wedge, okay, the streamlines would essentially incur a turn over here, and now I define my local x direction in this sense, which obviously you need to do because your scaling and the dimensional and your non-dimensional equations of the boundary layer relies on on the fact that your x direction has to be parallel to the direction of the plate. So if you want to apply the boundary layer equations just as we did, you cannot take the x direction in this direction. Then the scaling analysis that we did, or the order of magnitude analysis, will change accordingly, and your equations should change. So the bottom line is that you need to take your x in this direction, which means that now your u infinity will be a function of x in uh, outside the inviscid, outside the viscous region. Okay, that's so now the natural question arises that what is the choice of u infinity if so it becomes a function of x. Okay, and that's why this u infinity is chosen from the potential flow theory as some constant times x to the power m. So it's just it is chosen as a polynomial function of m. Okay, where this m bears the signature of this wedge angle, which is beta uh, primarily. Okay, so this means that this beta and m are indeed related by this relation. Okay, this you can obtain from the Faulkner-Sken solutions. I will not explicitly show it here, but I hope you understand that. All right. So what we will do now is we will apply the Euler's equation, as you guys know, in the inviscid region, as we did, and we can eventually show that this dp by dx is basically equal to minus rho times u infinity times du infinity by dx. So this is something that we did in the last class, and that's why I have directly written it. Which now means that if I write the x momentum equation, this means instead of the term dp dx going to 0 for the case of a flat plate, now we will have a non-zero pressure gradient of this form, which is a function of u infinity, as you can see here. Okay, so this is now my modified x momentum equation, and precisely this equation, if written in terms of the stream function and you follow exactly the same approach which you did for the Blasius solution, will give you the Faulkner-Sken wave ODE that you basically saw. It's again a third order ODE. The limiting case of that ODE is that. So can you tell me what's the limiting case? What is the limiting value of m? Okay, which where if we substitute that value of m, the Faulkner-Sken solution uh, basically simplifies to the Blasius solution. Can you tell me that? What's the value of m? So I'm asking that what should be the value of m if you substitute that in the Faulkner scan ODE, if you remember, the Faulkner scan ODE is also a third order ODE, similar to that of a Blasius ODE, just that there it bears the signature of the wedge profile. But my question is, what should be the value of M for for a Faulkner scan solution to reduce to the Blasius solution? So, can you tell me? That's simple, right? So just think about it. Just think about it. What happens in case of a flat plate solution? In case of a flat plate solutions, our U infinity is a constant, right? This means, so from here, can you tell me what should be the value of M just from this definition of a flow over a flat plate? So I means that for a flat
Zero,
plate, yeah,
zero.
exactly. So it means M has to be equal to 0. Okay, in case of a flat plate. So you can verify it yourself that if M is 0, we retain the Blasius solution that we commonly know. Okay, so now let's do one thing and we will slowly understand how this. So now at least you understand that this dp dx is essentially a function of the wedge profile, which, so it's a function of M, and this M essentially depends on this beta, which is the wave angle. Okay, so now we'll do a short exercise and then you will basically try like understand how this dpdx essentially changes with the changing wedge angle, and this you will, and then you will understand how does adverse pressure gradient or favorable pressure gradient come into this picture. Okay, so we saw that from this equation, that is, I hope this equation is clear. I don't need to derive, I don't need to tell you how did I get this equation. This is very simple, we did in the last class. So what we saw is from equation 1, what we saw is that dp dx is basically equal to minus of rho times u infinity times du infinity by dx. Okay, and I know u infinity bears the signature of that profile c times of x to the power m, which means if I substitute the values here, if I evaluate du infinity by dx, I would get what? I would get cm times x to the power m minus 1. Okay, and then I substitute these values here, and then let's see what do we get. So this becomes dp by dx. Okay, this becomes minus rho u infinity is c times x to the power m, and du infinity by dx is what? It is cm. Okay, yeah, it is cm times x to the power m minus 1. All right, and let's just write the constants together. So I'll just write minus rho, this becomes c square, and then it is m, and this is x to the power twice m minus 1. Okay, which means I got dp dx as minus rho, which is density, c square x to the power m, sorry, twice m minus 1. I'll just take this term together, and m. Okay, so this is something that we got essentially. All right, so can you tell me which value in this expression would dictate the sign of dp by dx? I mean, which value, or I'll just put it in the other way, what parameter in this expression would
And
say us, yeah, m, exactly. So you appreciate that, right? Because this density, okay, this density is a constant, c square is essentially constant. Sorry, I mean density is positive, not constant actually. It's obviously constant, but the sign of the rho is positive. Okay, c square is of course positive. X time to x to the power twice m minus 1 is also positive, because we are looking in the plus x direction, of course. That is our so our coordinate basically starts from here. Okay, so this is x equal to 0, which means in this direction our x is positive in nature, which means even if this m is negative, x to the power twice m minus 1 would essentially be positive, which means, so what does this mean? This means that sine of dp dx, that is the pressure gradient, okay, depends on m. All right, which also means, so if we have a closure loop, which also means that if m is greater than 0, okay, This means what? So if m is greater than 0, which means dp dx would be of negative sign. Okay, this is obvious because this term is positive and this is greater than 0, which means dp dx would be of negative sign. And what does this mean? Is this a condition of adverse pressure gradient or a favorable pressure gradient? So dp dx less than 0 is a case of adverse pressure gradient or a favorable pressure gradient. So this is,
Favorable.
yeah, exactly. So this is a favorable pressure gradient. Yes. This means this is a case of favorable pressure gradient. Okay. On the contrary, if m is less than 0, this will mean dp dx is greater than 0, and this is a case of adverse pressure gradient. Okay, so this is what the theory says to us. But try to understand how do we know? So let's say you are designing a plate or you are designing a wedge, and you try to understand. Okay, you try to understand that if there is a flow of a fluid over that wedge, will there be a separation or not? Okay, so this means, so what on what control? So what are the parameters do we have controls on? So we have controls on beta, which means we can choose a particular beta. If we choose that beta, we know the value of m, and for this value of m, we will see what is the sign of dpdx. Okay, so this means that we will certainly look into certain examples, but which means that indirectly it is not the dpdx that we initially like focus on. It is the wedge angle that we focus on, and from the wedge angle we try to see what is the pressure gradient that actually results in from that value of wedge angle. Okay, if dpdx is less than 0, we are in a favorable pressure gradient zone. If dpdx is greater than 0, we have adverse pressure gradient. Now, depending on the choice of the condition, that where do we want to use the wedge, we will then try to analyze that whether there will be flow separation or not. Okay, this is the second thing that we do, but this is how the flow separation, which may be caused by the adverse pressure gradient, is related to the wedging. Okay, I hope this is clear. We will look into certain examples. So this I took it from the book of, so the name of the book is Viscous Fluid Flow by F.M. White. You can find this in the book. So you can easily see that this is something that we summarize, that if beta is greater than 0, this implies m is greater than 0, that you can quickly correlate. And then this means our d infinity by dx is less than 0, and we are in a zone of favorable pressure gradient. And this is the reverse scenario that we are trying to talk about. And here they have given certain example. For instance, at this value of beta, okay, so again these are obtained once you solve the Faulkner-Skein solution. Okay, that is what they do basically. They just try, so you put in a value of beta, try to see. So basically what you do is you solve the velocity profile from the Faulkner-Skein solution, substitute the value of beta, and see if there is an inflection point or not. If there is an inflection point, there has to be a separation. Okay, that is what they that is essentially the idea how they do and how they essentially find out this solution. Okay, but this is actually a summary of the solution that they have. For instance, at beta around minus zero point 0.2, at beta around minus zero point 0.2, you see that a boundary layer has a separation. So a wedge angle of this magnitude, okay, is bound to have a boundary layer separation. That's something that you can conclude from there. Okay, and here as you can see, for beta equal to 0 and m equal to 0, we get the case of a flat plate. And here we get here are the other examples for this thing. Now let's quickly see two examples that so this will help us to visualize, where I have taken two cases. Okay, one where there can be this flow separation, and where there cannot be a possibility of flow separation. For instance, the beta angle is essentially measured in an anti-clockwise sense from the x-axis. For example, if we take a wedge flow, the beta here, or I mean the scale beta, as you can see, because there is a pi by 2 factor multiplied with, but nevertheless that's a constant. That's why I'll just say it's beta. So here the beta essentially is positive, right? Because obviously this is in the first quadrant, which means that the value of beta here would be positive. And if beta is positive, as in this case of a wedge flow, you will not see, as I said, you will not see flow separation here because we have a favorable pressure gradient, and this is indeed observed. Okay, for instance, if there is an aerofoil which is of this shape, okay, you don't see flow separation up to this region, and this is something that you guys would appreciate. Okay, up to this region you don't see flow separation, but in the wake region this is something that happens. Like, so the wedge angle is essentially negative because now for this, for an expansion corner, the wedge angle is measured in this sense because it's in the below quadrant, which means that beta is now negative, and then the pressure gradient is essentially positive, which means there is a chance of flow separation. Now, whether a flow separation will take place or not, that depends on the inflection point. But yeah, this is how it's actually related to how the wedge angle is essentially related to basically the fact that whether there will be a separation or not. Okay, so that is typically, as you can see, these two limiting case, or you can say these two seemingly different examples again explains the fact that why in the front side of an aerofoil, if there is a flow and in the front side of an aerofoil which is basically shaped, let's say like this, with having bearing some angle of attack, let's say, so this in this region, okay, in this region there isn't any flow separation, but there is flow separation in the wake region, and that typically explains the nature. Okay, so I hope you got what I mean to say, and if you have any questions on this, I would be happy to address. So this is something up to here. So you don't need to learn more than this, I feel. So if you have an idea of this, of the problem up to this point, how basically the flow separation is related to the pressure gradient, this is sufficient and this will suffice the cause of the subject. Okay. I'll wait here for some time. And with this, we end. If you have any questions, you can obviously ask me. I'll wait for 2-3 minutes here. If you have any questions, you can ask. And with this, we will end boundary layer. And today we'll begin a new topic, which is essentially a very important topic known as hydrodynamic stability. And we will solve a stability problem similar to the one that we solved, which is a bit little bit different in the nomenclature and maybe different in the approach, but it is similar to the one that we solved, and we will see, and we will solve that problem systematically in today's and the next class. And yeah, that's the objective of today's exercise. Okay, we'll stop here for some time, and if not, if you have any questions, you can ask. If not, we will start learning about boundary layer theory. Uh, Sorry, not boundary layer theory, hydrodynamic stability in 2-3 minutes. Meanwhile, I'll just come in 1 minute. All right. If you have any questions, you can ask, or else we will proceed with the stability analysis that we thought of like doing today. I'll just draw a schematic here in the meantime. All right. So today we will basically start something which is known as hydrodynamic stability. This is something that you have seen in the theory classes, that we will see that given a flow, if we add certain perturbations essentially means disturbances to that flow, that the objective is under certain assumptions. For instance, we take we stay in the regime of linear stability analysis and things like that. And under that regime, we see that the disturbances which we add to that particular flow, which already existed, essentially grows with time or decays with time. Okay, or like the vice versa. They might decay, they might grow with time or they might decay with time. Okay, this is something that we check. So this is essentially the principle of hydrodynamic instability, or you can say analysis of hydrodynamic instabilities, or whatever name you wish to say. But this is primarily the goal uh, of the stability analysis that we are supposed to do. And it's not just, so I reiterate that linear stability analysis is not just limited to this. I mean, stability analysis is not just limited to linear stability analysis, but for the sake of ease of calculations and for the sake that our equations and our like algebra is analytically tractable, and so that we can solve the equations, we resort to linear stability analysis. There may be certain instances, or there may be certain stability problems where linear stability analysis might not hold good. So can you give me an idea? Can you give me an idea on which instances linear stability analysis, from the name itself, might suggest, as it may suggest. I mean, it says you that these are certain instances where linear stability analysis might not hold good. So do you have certain ideas on that? I mean, what should be?
Weather
Yeah, go on.
weather forecasting.
Yeah, exactly. So yes, that's a specific example, but in principle, in the words of physics, if you say, if you say that if your disturbances are very strong, for instances, weather forecasting problems and all, with the perturbations are very strong with respect to the base flow. So if the magnitude, so you must understand that if the magnitude of, let's say, the perturbations. So for instance, I will denote the perturbations as the perturbation variable as small u, and I will denote the base variable with an index b. So for linear stability analysis to hold good, the magnitude of the perturbations, okay, should be very less than the magnitude of the base variable. Okay, this is the condition for linear stability analysis. Okay. See, we will see very shortly why this is the case. Okay. That is simply because when you linearize the governing equations that governs the how the perturbations essentially evolved, we will neglect certain terms which are non-linear in nature. Okay. That neglect, or that omission of those terms is only possible if the magnitude of the disturbances are very less than compared to the base flow. Okay, so here again, the first one of the terms that you oftenly will hear, as you guys have done in the theory classes as well, is something known as the base flow. Okay, base flow is essentially the flow on which we are adding the perturbations. For instance, as you can see in this figure, okay, we will try to seek the stability analysis of inviscid parallel flows. Okay, in class, you have done the stability analysis of viscous parallel flows, and you have reached something which is known as the Orr-Sommerfeld equation. That's a very famous equation. And in the Orr-Sommerfeld equation, if you invoke the assumption that your flow is inviscid, you will get something which is known as the Rayleigh stability equation, and we will derive the Rayleigh stability equation in this exercise. Okay, which will add to your which will add to your under it may add to a better understanding of stability analysis, and we will see a different route as well. I mean, the procedure is exactly similar to the one that you did in the theory classes, but this is a different aspect of studying the stabilities of inviscid flows, rather than simplifying the Orr-Sommerfeld equation and then getting the Rayleigh stability equation. Okay, but nonetheless, the procedures that you did in the theory classes is basically the same, okay, with the one that we are supposed to do today. All right. So So for instance, I was telling the definition of a base flow. So which means that if we are, let's say trying to understand the linear trying to understand the stability of inviscid parallel flows, we can assume that the base flow is generated by a flow which is basically flowing through two parallel plates, or let's say if we are in a cylindrical geometry, it's the flow through pipe basically. So this means that although I have shown this as a general profile, you can assume this as the profile that you know, which is the parabolic profile. Okay. In other words, although I have represented in a generic sense, the knowledge of base flow is completely known to us, which means that this base flow and the base pressure should be known to us, or we should be in a position to evaluate them radially and then try to evaluate what the governing equations of perturbations look like. Okay. Do you have any question on this? We'll stop here for some time as this is a new topic. We'll go very slowly. We'll stop here for some time and then we will try to follow the procedure step by step. Okay. But before this, I would just state the assumptions. Yeah. Okay. I'll just state the assumption.
This base
Yeah. Yeah, go on.
this base flow is always a steady state solution.
Yes. So typically, yes. Generally, the base flow is a steady state solution because we are looking. That's one like assumptions. In fact, that I was supposed to write. So in linear stability analysis, we assume that the base flow is essentially steady in nature, and yeah, that's an assumption essentially. There may be instances where the base flow might not be steady, but that is not the scope of analysis within the linear stability problem. Okay.
Then like periodic flows there based it how we can get out.
Correct. So in periodic flows, if you can consider time as a parameter and not as a variable, I think then you may do a linear stability analysis, but typically we will not go into that complexity. Like we will, so anyway, even if there is a so in case of periodic flows, generally you can treat time as a parameter. Okay. That's the first thing. And if it is not periodic and it's an arbitrary transient flow, then you can always have a quasi steady problem, okay, where you do the analysis for a time for a very small interval of time where your flow can be assumed to be steady, and then you do the perturbation analysis, okay. So this is something that you can do. But so far as I know, we generally resort to taking steady base flows in this analysis, or else you can do the analysis maybe, but that so the algebra or the math or the like like the scope of understanding that or the clarity of understanding that we get might be little difficult in studying. That's what that's what you can see. I'll look into it. Maybe if there's a certain examples of periodic flows where you can have periodic base flows where you can have perturbations, and then can we come up in a uh, can we come up with a solution of linear stability analysis to that problems? I'll have a look and let you know in the next class. Okay, is this fine?
Yeah, yeah.
Yeah, sure. All right. So we will start with the assumptions. So first we'll, as I said, it's an inviscid analysis, although this can be extended to viscous flows as well. Okay, which you guys have did. But in this exercise, we will essentially assume that the flow is inviscid, and of course, it's incompressible. One important assumption is that we will assume the base flow to be unidirectional. This assumption again makes sense because we are looking into the stability of parallel flows, which means the base flows, that is the streamlines, essentially are parallel or nearly parallel with respect to the walls, and that's why we can uh, rest assured that the base flow would be unidirectional in nature. Okay. The third assumption, as I said, is an important assumption. Okay. For instance, we'll assume that the base flow is steady. All right. So these are the assumptions on which we will work on. Okay. And then we will start off with our analysis. So the first step, so we will proceed very sequentially and very systematically on this because there is a lot of math that is involved in stability analysis as you have seen also. So we'll proceed very slowly. So so the first step, okay, one second. Just one second. I think I've turned some microphone on. It's off actually. All right. Okay. So in step one of our analysis, we will start off by writing the governing equations that govern the total system. Okay. So can you tell me what is the governing equation that govern the total flow? And the idea is that we will subtract the equations of the base flow to get the equations for the perturbations. Okay, so this is the first task that we need to do. But before that, we need to know what are the governing equations for the entire flow field. So can you tell me what the governing equation?
Continuity and
Yes.
momentum.
Yeah. So momentum means what? Is it the Navier-Stokes or
Navier-Stokes.
Navier-Stokes? Is it?
I mean, if it is in Viscous Euler,
Yeah, exactly. So it's the Euler's equation and the continuity equation, right? So the first step is the continuity equation, and w- as a part of this like exercise, we will denote. Okay, we will denote the total the total flow which comprises of the base flow plus the perturbations as capital uh, as a capitalized variable. Okay, and then this dash the dash terms that you see here, this will denote dimensional terms. Okay, we will also non-dimensionalize our problem as you will see for the sake of simplicity. You can also solve it dimensionally, it's up to you, but we will non-dimensionalize our problem and we will denote the dimensional terms as these dash terms. So again I repeat, the capital variables will be our total this will be our total flow variable. The variables with the subscript b, okay, this will be the base variables, and our small variables will be our perturbations. Okay, and if there is the dash over the variables, this means it's a dimensional variable, and we will use certain characteristic variables to non-dimensionalize the pertinent dimensional variables. Okay, so bear that in mind. So the continuity equation is basically this. It is divergence of velocity. Okay, this is the continuity equation, where again I repeat, this capital V is essentially the total velocity that we are denoting here, which is of course dimensional in nature. Okay. Then, as you said, we have the Euler's equation. We have the sorry, we have the Euler equation. Okay, which you know is basically this. It's del V by del T of the total variable plus V dot grad V, as you have seen it multiple times, and this is equal to minus of 1 upon rho times gradient of the pressure. Okay, so I hope these equations are clear to you. All right, so just for the sake of clarity, I would write that uh, just for the sake of clarity, the total velocity field which we denote it by capital V. Okay, this is essentially a function of x. It can be a function of y. It can be a function of z. It can be a function of time. Why? Because this total field has two terms. One, the base variable, which is a steady variable in as a function of z plus the perturbations, which we will denote it as a small v. Okay, and that's why the total variable v or v prime is essentially a function of the coordinates as well as time. Okay, And this total variable can be now decomposed, okay, into the base flow, which is this u prime, which is essentially a function of z only, plus the perturbations, which we will denote it as small v. Okay. And these perturbations are a function of space, as you guys know, and time. This has to be, because you don't know how the disturbance propagates, right? You just can't tell that if your base flow is in the z direction, this essentially does not mean that your disturbance will just propagate in the z direction. This can propagate in the x, y, as well as in the z direction, and this can be essentially unsteady in nature, as we will see. This, of course, has to be an unsteady, because they might decay with time or they might grow with time. Okay, depending on how there is certain, so that there is something which is known as an eigenvalue, and depending on actually the nature of that eigenvalues, you can tell whether the disturbances grow in time or decay in time. We will see all these things subsequently, like, and in the subsequent like steps. Okay, but yeah, so this is the total velocity field, and similarly, the pressure field, which is again the total pressure field, of course. The pressure field, you can similarly write that P prime, yeah, this has to be prime because these are all dimensional now. We will non-dimensionalize it later on. Yeah, so P prime as a function of x prime, y prime, z prime, and t. This is also equal to the base pressure, okay, plus the perturbations in pressure. All right. Okay. So now what do we have? So the step one is completed. We have written the governing equations which govern the total flow field. Okay, we will name this equation as 1. We will name this as 2. Okay. And then the next step is to evaluate. So what's the next step? Can you tell me? What could be the possible next step?
Base flow satisfies
Yeah,
the
exactly,
equation.
exactly. So exactly. So the next step is to find out the base flow equation, and you will eventually see that the base flow essentially satisfies the Euler's equation. Okay, that we will basically see. So, but in generic, I will just write that find out the base flow equations. Okay. So the idea is, since the total flow field, since we are dealing in flow, I will use two variables basically, one for the flow field, that is v, and one for pressure, that is p. So since you know that the total flow field and the total pressure satisfies the Euler's equation, which means the base flow has to satisfy the Euler's equation, and then we will see that what we end up getting. So if we just write the Euler equation, what do we get? We get, so remember, our base variable will denote it as b. So this is what the base flow satisfies. Okay. So I'll just first write down the Euler's equation. All right. So now, can you tell me, is this the entire equation that the base flow satisfies, or there is certain simplifications here?
Time derivative 0.
Yeah. Yeah. This is 0. Is that all?
And also, this no
How about this term? Is it 0 or non-zero?
uh, this is also 0.
Exactly. This is 0. You can, so if you just expand this term, it's 0, because this term, let's say you are writing it in the x direction, would be u times del ub times del ub by del x. But we know that this ub is just a function of z, which is the cross stream direction. Okay. So this term is also 0 for the equation of base flows. Okay, which means that for the base flow, I just end up getting this gradient of PB, which is the pressure, which is the base pressure, is equal to 0. So what does this mean? What does this mean?
There is no pressure gradient
Yes. Or
across
yeah,
the.
yes, exactly. Which means that there is no pressure gradient. This means This means that PV
Number.
prime is a constant. Is Can you say this?
Yeah.
Which means this is equal to some reference pressure P naught. Okay, and this is of course true because see, if there is an inviscid flow, okay, if there is an inviscid parallel flow, okay, there is no, it is obvious that there has to be no net force due to pressure. That is something that you can understand, okay, because had there been viscosity, the viscous force, the pressure gradient is being balanced by the viscous forces, okay, but we know that this is an inviscid problem, which means that if there is an inflow of an inviscid fluid, okay, the net force due to pressure has to be equal to 0. So this is essentially a consequence of the fact that the flow is invisible. Okay, so I'll write down here that
And also, is it like these are all momentum driven flows, not pressure driven?
yes, essentially yes, true. That is again a conclusion of the fact that gradient of P is equal to 0. Yeah, all right. Yes, that is true, of course. So I'll just write it here that for an inviscid flow, okay, the net force due to pressure is 0. See, it's very obvious and it's very like easy to understand because see, when you are, so let's not worry about how you are generating this flow. But once by some mechanism, it's correct that it's driven by momentum, of course. But let's try to understand it this way. Okay, once you are generating this flow by some mechanisms, okay, in the steady state, this flow will always sustain. Do you understand that or not? This means that there is no mechanism whatsoever that is present in this channel that will retard the motion of this flow. Okay, that's why you that's why the net force that's since it is inviscid, the net force that arises due to pressure has to be equal to 0. Okay, and this like flow, if it is inviscid, it will always sustain inside the channel. So that's another way of telling that gradient of P is equal to 0 in this case. Okay, I hope you understand this. All right. So we have, so what? So we proceed these things very systematically. So first of all, we derive the equation that governs the total flow field. Then we saw as a consequence of the base flow satisfying the Euler equation, the net force due to pressure is 0. So the third step, the step that is that I would say it should be done prior to the like step of calculating the governing equation for the perturbations is that we will non-dimensionalize the equations. We'll do a non-dimensional analysis, and this essentially helps us, and we will see this. Okay, so I'll say the third step. Okay, I'll say it's non-dimensionalized, non-dimensional, or what do you say? It's in non-dimensionalize the equation. All right. Okay, so we have done this many a times. So now you need to tell me, do we have a characteristic length scale of this problem? Do we have a characteristic time scale of this problem? Do we have a characteristic velocity of this problem? Okay, first you need to tell me this. Do we have a length scale here?
Yeah,
Yeah,
diameter of pipe.
yeah, exactly. Or so if it's a channel, it's the height of the channel.
It's a
Okay,
height
yeah.
of the channel.
Do we have a characteristic velocity scale here? Do we have
We
that?
can take U average or
Yeah,
U
exactly,
max,
exactly, exactly.
center
So,
line.
yes, exactly. So we do have, because in a way the base flow is known to us, right? Which means you can take either the average or the maximum as the characteristic velocity. Okay, good. So we will take the characteristic length scale as L naught, which is basically the channel height. And we will take the characteristic velocity as, let's say, you can take average, maximum, or average. Okay, either of these things you can take of UB jet prime. Okay, anything will work here. Okay, if this is the case, even if we don't have, okay, even if we don't have an inherent time scale, we can define a characteristics time scale as LC by UC. Okay, you can also define a diffusion time scale of this problem. That's completely up to you. Okay, your approach and your dimensional equation that you derive at the end will exactly remain the same, just that you might have some extra terms which so extra terms with some extra terms which bear the ratio of the diffusion time to the advection time. Okay, this you might have if you change the time scale to a diffusion time scale, but we will follow the advection time
But
scale of this problem. Yeah, go on.
but here there is no
Yes, yes,
viscous.
exactly. Yeah, exactly. Yeah, that completed ran out of the mind. Here there is no viscosity, so the only choice of time scale that you have in this problem is the advection time scale. Yeah, true. But in the Ore-Sommerfeld equation, in the generalized equation, you can also choose a diffusion time scale as your this as your inherent time scale. Okay, I mean as your characteristic time scale. But yeah, you are absolutely right. Here it's an implicit analysis. It just completely ran out of my mind. Since it's an implicit analysis, the only time scale that you have is basically the advection time scale, which is LC by UC. Okay, this means that since your LC is L naught and your UC, let's say we are calling this as some, what do you say, some V naught, let's say. I'm telling that this UC is some V naught, which where V naught is the average or maximum of the base flow. And that's why this would be some, let's say, V naught. Okay. So if this is the case, can you tell me what is the characteristic pressure now? Because we also need the characteristic pressure here, right? In order to non-dimensionalize this. Can you tell me what would be the characteristic scale for pressure? We saw that in the second or third class. Yeah.
Rho v
Yeah, exactly.
rho v square.
Yes, it is rho UC square, okay? Which
Uh,
is rho times V naught square. Okay. All right. Now, since we have done defining the characteristic variable, we will now define the non-dimensional pressure P. Okay, remember, if I write the capital P, it's the total pressure which I am talking about. Always remember that. The total pressure is basically the dimensional pressure by PC, okay, which is nothing but P dash by rho V naught squared. Similarly, as we have done many a times, the non-dimensional x, okay, the non-dimensional x, that is the length, is the dimensional x, okay, divided by LC, which means it's x prime by L naught, let's say. And the non-dimensional time t is basically t dash by tc. All right. So I hope this is clear. I hope you are clear to this point. So as we know, you can very easily so that if you substitute these, we will not do the math now for the substitution of the non-dimensional variables in the governing equation to derive the equation for, sorry, the substitution of, I mean, changing the dimensional variable into the non-dimensional variable using the characteristic variable. We all did this many a times. So I'll just straight away write down with the non-dimensional counterparts of the dimensional equations governing the total flow as something like this. So you can show that uh, your continuity equation would be just divergence of the non-dimensional velocity equals to 0, as we have seen. And your Euler equation, okay, is again something like this. It is just, you can just check it by yourself. You'll get these two equations once you substitute the non-dimensional variables in place of the dimensional variable. Okay, minus gradient of p. All right, we will name this equation as 2. Sorry, I hope this should be 3 because we had 2 over there, and this is equation 4. All right. So now we have derived the governing equations of the total velocity, total non-dimensional velocity, and the total non-dimensional pressure, uh, which essentially are the continuity and the Euler equation. Okay, so what we did is, so let's quickly recapitulate. So we started off with the dimensional versions of the total flow field and a total pressure field. Okay, we basically derived the equations that govern the base flow, and we saw that the net force due to pressure is 0. We use the characteristic variable to non-dimensionalize the equation that govern the total flow field. Okay, the next step, of course, is to derive the equations that governs the perturbations or the disturbances. But before that, I would again like to highlight that this total flow field V in non-dimensional terms. Hold on, in non-dimensional terms. Okay, this is again the base flow, which is u of z Okay, and this is in the x direction, plus the disturbances. We will write the disturbances. So let's just do one thing. Let's write the disturbances as start variable. Okay, this will help us. This will help us to significantly like distinguish terms, because somewhere I might use a small variable in place of a capital variable, and then this might create confusion. Okay, so remember, whenever there is a subscript b, okay, whenever there is a subscript b, yes, that's a b here. So whenever there is a subscript b, that's the base flow. Whenever there is no subscript, that's the total flow field. And whenever there is a star, that's so a non-dimensional variable with a star denotes the perturbations. Okay, and that's why I just wrote it here. So we will denote the non-dimensional perturbations as some v star, small v star, and this is again a function of x and time. Okay, and similarly, the total pressure P as a function of x and t is P naught, because we have showed that the base pressure just reduces to a reference pressure P naught plus, and of course, since it's non-dimensional now, let's write this as P naught bar, because if our reference pressure is P naught, then P naught bar is just P naught by PC. That's it. Okay. So it is P naught bar plus some P star of x and t. So this are essentially the decomposition of the total flow field V and the total pressure P in terms of the base variables and the disturbances, now written non-dimensionally. Okay. We'll name this as equations for A and B. All right. So we have proceeded very slowly, and I hope you are with me with this, and I hope everything is clear up to this point. So as I said, the next step now, that is the step 4, okay, is to derive linearized governing equation for disturbances. So sometimes people call it disturbances, sometimes people call it perturbations. Okay. And how do we do that? Can you tell me now? How do we derive equations for disturbances?
Subtract total
Yeah,
equation
exactly.
from the base state.
Exactly. So what we do is, you are absolutely right. So what we do is we take governing equation for total flow, okay, and subtract the governing equation for base flow. And once we do this, what we get is something that we need, is nothing but the governing equation for disturbances. All right. But always remember that in doing this step, as an additional part of an exercise, okay, as an additional part of an exercise, what we will do is we will also linearize the governing equations for disturbances. Okay. So why we are doing it? Since we are trying out linear stability analysis. So what we will do is, once we do the subtraction, that we subtract the governing equation of the base flow from the total governing equation, we will get the governing equation for disturbance. Okay, but that won't help us so long as we don't linearize the problem. Okay, because since we already said that we are looking for linear stability analysis, which means that I would just give an example. So once we do the subtraction, let's say we subtract the x momentum total that is the total x momentum equation minus the x momentum equation from the base flow, and we don't have any x momentum equation in the base flow, which means the total momentum equations for the total flow is nothing but the total I mean that. So it's the equation that governs the perturbations as well. Okay, and in that equation what we will see is you will eventually you will see certain terms like something like this. Okay, let's say it is v star times del u star by del x. Okay, where v star is the, so it's the y direction disturbance velocity, u star is the x direction disturbance velocity, and you will see that once you do that subtraction you will see certain terms like this. But as you see this term that you see here, oops, that this term that you see here, this is a nonlinear term, right? So why this is a nonlinear term, can you tell me?
Both very perturbation are
Yeah,
multiplied.
because exactly these perturbations are not known, right? These perturbations are something
Yeah,
that we are trying to
unknown.
find out. So since these are unknown, okay, we will we will omit or we will cancel certain terms. Okay, so what I mean to say is that, so this is one kind. Okay, when you, so when you do the subtraction, you can try out yourself because we have already done that. You will see that this is one kind of nonlinear term in disturbance equation. Okay, and what we will do is we will neglect these kind of terms. Now can you tell me, will we neglect this term or not? Oops. Can you neglect this term where this
No,
u?
that was base.
Yeah, yeah, exactly, this u is the base flow profile. Okay, can you neglect this?
No.
No, right? Yeah, exactly. We cannot neglect this because this is not a non-linear term. Because again, I repeat that we have complete knowledge of the base flow. Okay, which means this again is a non-linear term. Okay, so I'll just write these kinds of terms. Okay, these kinds of term we will retain. Okay, yes, all right. So I'll not show the math because linear stability analysis is a big like exercise. It's very simple. Just substitute the form of the total velocity and total pressure into the equation that governs the disturbances, and then just discard the terms which are nonlinear in nature. Okay. So once you are done with that, okay, I'll just straight away write the linearized equation for disturbances looks something like this. Okay. So the x momentum is like this. Okay, so the x momentum is something like this. So it is u star times del u star by del t plus the base flow times del u star by del x plus w star times del u by del z. Okay, is this a linear term or a non-linear term? Can you tell me?
Linear.
Yeah, exactly. That's why we retain this term, and then we have just this term minus del p star by del x star. So again, I have just not shown the math. You can very easily do the math, and then you can see that just discard all the nonlinear terms. For instance, as you can see, as you can see here, we also had a term which is let's say what. So of course we might have a term which is del u star by del y times v. We may have this term, but then we can simply neglect this term. Okay, because it is essentially a non-linear term. I hope you can understand that because this term is what. So you understood that, right? How this equation is obtained? Did you understand? Or I need to show it?
No, understand.
Yeah, exactly. Again, I repeat, like, So this term that you see is nothing but v dot grad v. Okay. When we expand, we are supposed to get three terms. Sorry, I think there's a delay in this thing. Okay, that's fine. Okay, so when we expand, we are supposed to get three terms. Okay, so first term is this that we all know. The second term would be just v star times del u star by del y. But as I said, this term is essentially non-linear. We just looked above. Okay, why? Because v star and u star are both unknown. Okay, and that's why we have just discarded that term. The third term is of course not a non-linear term. Sorry, the third term is a linear term. That is simply because this u, which is the base flow profile, is known to us. Okay, and that's why we just have these two terms and cancel the middle term. I mean, cancel means we ignore the middle term on account of the linear stability analysis that we are doing. Okay, and then we have the pressure term. Of course, the pressure gradient is a linear term, and that's why we have del p star by del x. All right. So this is the x momentum. Similarly, we have the y momentum. Okay, the y momentum would be del v star by del t plus u times, it's similar, del v star by del x. Okay, and you can show that here the two other terms, that is v star times del v star by del y plus w star times del v star by del z would be 0, again owing to the account of linear stability analysis. Okay, and this is equal to minus del p star by del y. Right. All right, and of course the third term, which is the z momentum equation. Okay, it is, this is y momentum and this is x momentum. The z momentum is again similar to the y momentum, which is del w star by del p plus u times del w star by del x equal to minus del p star by del z. All right. So we have done one more step. That is, we just went into another level. So let's say this is equation 5 ABC. Equation 5A. This is equation 5B. And this is equation 5C. So now what we did is, from the base flow equations, we linearize the base flow equation and obtain the linearized set of base flow, I'm sorry, not the base flow, the disturbance equation, which are equations 5A, 5B, and 5C. All right, we'll stop here for some time. If you have any doubts, you can ask me, and or else we will proceed with some.
Continuity.
Yeah, yeah, of course, we will use the continuity also. That, yeah, that's true. That's true. Of course, we have the continuity equation. But later on, we will see that. I think you know that we will use something which is known as the squares transformation, which changes a 3D disturbance problem into a 2D disturbance problem. We will see what squares transformation is, maybe in the next class. And then we will see that once we are in a 2D problem, since we are in a 2D problem basically, by the use of the squares transformation, we will eventually use the stream function approach. Okay. Uh, so not the stream function here, but we will use, I don't think we will use the stream function here because, just hold on. Yeah, we can, yeah, in fact, we can use the stream function, but anyways, yeah, there is no harm in using the stream function so long as your continuity is satisfied. But yeah, anyways, we will see that once you use the stream function approach, the continuity is inherently satisfied, and that's why we don't care about the continuity equation much. But in principle, yeah, we should also write the continuity equation, which is basically this. Okay, plus del v star by del y plus del w star by del z is equal to 0. Maybe I should name it as type D. All right. Yeah, of course. We need to use the stream function. That is simply because, like, once you reduce it to a 2D problem, the only resort that you have is to use stream function to solve your problem, basically. But anyways, that's a later part that we'll do. But in principle, we have four equations, which is the x, y, and z momentum and the continuity equation. All right. So we'll stop here for some time. If you have any doubts, you can ask me. or else we will proceed with the next step. So this is step how much? This is step 4. We'll proceed with the next step here. Okay. So can you tell me what would be the next step? What do we do now? Are we
Assume one
yeah,
form of
yeah, exactly. So what is that form called? That form essentially has a name actually. Can you tell me what is that form? You are true. We assume a form, but that form has got a special name actually. I'll tell you what that name is. But before that, see, we still have not done one more thing, that is, so we derived, so what we did, so this is, so the steps are very simple. So what we did is we derived the equations that governs how the disturbances basically go. So we derived the governing equation for disturbances, right? But still we have not derived the boundary condition for disturbances, so that is something that we will do later on. That is one task that is left. But before that, just appreciate the fact that we have not, so what, so the goal is to evaluate this u star, w star, v star, okay, because these u star, w star, v star are the function of x, y, z and time. This is some, so the goal is to evaluate these things, and for this we need to solve these equations 5a, 5b, 5c and this 5d, okay, based on certain boundary conditions that we have. That is okay, and of course we need some initial conditions because there is also this time derivative, but so let's say we have that. But then also it poses a challenge to us, simply because these equations, that 5a, 5b, 5c, these are coupled equations, okay. Couple means that we see a w star here as well, we see a w star here as well, okay, we see a v star here, okay, p star is here, here and here, okay. This means this is a highly coupled, it's a highly coupled linear PD, linear set of PD. Yes, numerically you can obviously solve this using any finite, let's say you are using any CFD scheme like finite difference or finite volume or so long, whatever you use. But analytically, this is not solvable yet, because these are a set of coupled like linear PDEs. Okay, where the variables essentially varies with x, y, z and time. Okay, so it's not so straightforward to solve this, and that's why in order to have a analytical perspective of its solution, what we do is we decompose this variable u star, v star and w star, okay, into a certain form. That form is known as normal mode analysis, okay, or normal mode forms, okay. So what we do is in step 5, as we have said correctly, we will introduce normal modes, okay. Now why these are normal modes you will see very shortly. So what we will do is, let's say u star, which is the disturbance velocity in the x direction. This u star, of course, is a function of the x vector, which is this x vector is the position vector, let's say, which means this x can be written as x, y, and z, okay, and time, of course. So this is the variable. So what we do is we write this variable, okay, as a function of, let's say, u hat of z times e power some sigma t plus I kx plus ly, okay. So, so at the very first instance, there should be a thought that should come into your mind, that why this form only? We could have used any other form, right? We could have brought x here, we could have put z there, we could have brought x here, but why this form? So can you tell me why did we bring in z here? And but remember, before that, I would tell you that this sigma is something which we will call as the eigenvalue. This k and l, these are known as wave numbers, as you can see from this representation. Okay. So my question is, why do we write such form, okay, of the perturbations, and why this is known as normal modes? Okay, a similar like a similar problems we did while we were solving those transient analysis problems. So this is somehow related to that. You can think about that and you can answer, or else you can just give it a try. So can you tell me why? So why do we do this? Why do we do this normal mode analysis? Or like, okay, it's like we assume a form, but why only this form that we are assuming? Okay, this is something that you need to understand. Can you tell me?
assume that those will be all linearly independent modes which will be there. So each
Mhm.
disturbance will have its own history, and we can superimpose them.
Yeah, true.
And
Yes,
okay, that's why the normal modes,
yes,
model analysis, and this form we chose because our main profile variation is in the uh, like base profile. Major variation is in the z direction
yes,
compared to other uh, directions.
yes, true, true. You were like almost on the right answer. I would say 98% you are absolutely right. The only 2% is that how you frame the answer and how you told. You are absolutely right. Okay. See, the thing is, I'll just explain it here. So, of course, whatever you said, that is absolutely right. There is no uh, wrong answer in that. So the thing is, in the x and y direction, as you saw, okay, the disturbances. I mean, so what does modes mean? The modes mean that at each and every value of k and l, we'll have disturbances. So for each and every value, independent value of k and l, we will have disturbances. Okay. So in x and y, which is basically this and this, in these two directions, there is no restrictions to the number of modes that a disturbance can have. Okay. It can have, so it can have k modes, k's modes, and it can have l's modes, because I mean, what I mean to say that it can have k1, k2, k3, let's say up to kn. Okay. So this means that, let's say one disturbance in the x direction, okay, let's say have a wave number which is, let's say, k1. It can also have, so there could be another disturbances which is equally present in the x direction, which will have a different wave number k2. And in general, in general, okay, both these situations can be possible, and this same logic applies in the y direction as well. But in the z direction, the flow is limited by the appearance of that base flow, okay, as you have said, which means that we cannot have all the generic wave numbers in the z direction. Okay. And with reference to this base flow, we try to see what modes of disturbances in the other two direction that could appear as a result of the base flow that we have. Okay. And this is, I think this is something that you already said, but I just like gave some, like, what to say, gave some structure to whatever you said. But yeah, this is exactly right. Okay. And that's why we have that kx plus ly. Okay. And why do we have that sigma term then? Can you tell me? We could have just written e power lx plus uh, ky. Why do we have that sigma term?
Same with time also. Time
Yeah,
also we have
exactly.
no restriction.
Yes. So the same thing is that the disturbances now can either grow with time or it can now decay with time. Okay. And it is precisely the nature of sigma, or in a good, like, or in a more clearer perspective, it essentially tells whether the real part and the imaginary part, of course we'll see that later on, but it is essentially the imaginary part of the waves of the eigenvalue of sigma, which dictates whether the disturbances grow with time or decay with time. Okay, we will see that shortly. But it is sigma essentially which tells us, okay, that whether my disturbances that we have, they will grow with time or they will decay with time. Okay. So a linear stability problem in the regime of linear stability analysis and using normal modes simply relies on finding the eigenvalues, that is sigma. Okay. And then just from the knowledge of sigma, we can rest assured and we can say that whether my disturbances, which we add here as, let's say, u v w, whatever we add here, and also to pressure, they will grow with time or they will decay with time. Okay. So that is something that you need to understand, and I hope you are clear on this. Okay. So similarly, so this is introducing normal modes in the x direction velocity. So we also need to do this in v star also, because v star is also a function of x and t, and this would be vk object times, yeah, this is, there should be a bracket here, or even if you don't use it's fine, and it's e power sigma t plus I times kx plus ly. Okay. And similarly, w star can also be written as w cap of z times e power sigma t plus I times kx plus ly. All right. So this, so the decomposition that you saw here the decomposition that you saw here is essentially known as decomposing the disturbance velocities into their normal modes. Okay, now we will do a small transformation here. Okay, we'll just do a small transformation. What we will do is we will denote sigma as minus I alpha c. Okay, where alpha is now a new wave number that we're introducing here. Okay, and we will also use this transformation that our k is alpha. Okay, and our L, which is the wave number in the which is the wave number in the like y direction, is beta. So why we are doing this? Because our analysis will become simplified if we do this transformation. Even if you just don't do this transformation and just keep sigma, k, and L in your analysis and just carry on, the algebra might be a little bit long, but you will end up getting the same Rayleigh stability equation that you seek to find. Okay, but just to make the algebra little bit short, okay, we will use this transformation here, where this C is known as the eigenvalue. Okay, this alpha and beta, as we have seen, these are wave numbers. All right, so this C that you saw here, since this is an eigenvalue, I can always write the eigenvalue as some real, because we can have either we can have a real eigenvalue. So a matrix can have a real eigenvalue and it can also have an imaginary eigenvalue. Okay, so in general, I will write the eigenvalue C as some real of C, as a real part, which is CR plus I times CI. Okay, this means what? So what does this mean? This means our sigma, okay, can be now written as minus I alpha CR plus I times CI. Okay, which means I can write it as minus I alpha CR plus alpha Ci, because I square is minus 1 and then there is already a minus here, which becomes alpha times Ci. Okay, which means this terms is nothing but sigma I, which is the imaginary part of the variable sigma, and this is nothing but sigma real. Okay, therefore, I'll so we can actually get a very interesting conclusion here. Okay, so I said that in this term, okay, in this term of the normal mode that we write, which which so I would say which variable dictate whether, so which variable dictate the stability? Can you tell me?
Sigma.
Yeah, sigma, right? It's this term actually essentially e power sigma t. Okay, which means if I now evaluate this e power sigma t, and then I just write e power sigma as this form, okay, which means it is minus I alpha CR plus alpha times CI, okay, and this is T, okay, and I can write this term as what? I can write that e power alpha CI T times e power minus I alpha CR T. I hope the math is clear. Okay, so I can write it as e power sigma t as something like this. So now, can you tell me what is the condition for stability based on this?
If imaginary part of Ci greater than 0, it is growing,
Yeah, exactly. So
and
that's
less
the
than
condition
0.
for exactly. So the Ci greater than 0 is a condition for instability. Ci less than 0 is a condition for stability. Right? Is that,
Yeah.
yeah, exactly. That's what I want to like convey. Okay. So as you have rightly said, the condition for stability is Ci less than 0. Why? That is simply because if Ci is less than 0, this so this term cannot, it's obvious that this term e power minus I alpha CRT, this cannot contribute to the growth or decay of disturbances, okay, because this is so this is a sinusoidal term, okay. It's like e power I alpha t can be written as sine of alpha rt plus I times cos of this term, okay, which means these terms would just be some oscillations. A disturbance, so the term that is responsible for a disturbance to either grow or decay with time is just this term, e power alpha CIT, okay. And the variable which is responsible, or I would say the part of the eigenvalue which is responsible for this cause is this Ci, because if Ci is less than 0, okay, you can see that this e power alpha CIT would decay simply because this would be some e power minus of some term, because all other terms are positive, which means the disturbances have to decay with time if Ci is less than 0, and if Ci is greater than 0, okay, it has to, so e power I alpha t would increase, okay, which means the so it's a case of instability, okay. So I'll just finish the writing. So it's, so the condition for instability is that Ci is greater than 0. All right. Okay. So do you have any doubts on this? First of all, like if you have any, you can ask. But I hope this is clear to you that so in a process of obtaining the solution, we have also derived what is the condition for stability and what is the condition for instability. Okay. So before ending, we will do one last step and then we will call it a day today, and then we'll proceed in the next class. So, but first of all, if you have any doubts, you can let me know, or else we will do one final step. That is, it's very simple. We'll just substitute the form of these normal modes in the governing equations of disturbances. Okay. And then we'll just stop here for today, and then we will continue it in the next class, of course. Okay, so if you have no questions, the last step that we would do today, but this does not mean that this is finished. We are yet to like finish a lot for this exercise, but the last step that we will do today is just substitute the normal modes in the linearized governing equation for disturbances. All right, so if you do that in the continuity equation, okay, so what was the continuity equation? It was this basically. And if you just substitute the normal modes of del u star, del v star, and del w star, you will see that your continuity equation eventually simplifies to something like this. You can do it and just check it yourself. The math is very easy, of course. Okay. We will name this equation maybe what? So these are, okay, this is 5abc. We'll name it as 6a maybe. Okay. So that's the continuity. Similarly, the x momentum equation, if you just substitute the form of the normal modes, you can just do it yourself and see. You will just end up getting something like this. All right. So this is your x momentum equation. 6p. Okay. And your y momentum equation is this. So again, I have not shown you the math. You can just do it by yourself. Just go on and substitute that in the equations that we derived. It's I alpha u minus c p cap of z to I beta times p cap of z, and the z momentum equation is basically this. It is I alpha u minus c into w cap of z. This is minus dp hat of z by dz. Okay. All right. So I'll name this as equation 6c. I'll name this as equation 6d. Okay. So we are, let's say we can say we are at the halfway stage of our analysis. So what we did is, let's just quickly recapitulate. So the step one, what we did is we just started off with a governing equation for a total flow field. And step two, we evaluated what would be the base flow equations be like. Step three, we used the non-dimensional approach. Step four, what we did is we evaluated the governing equations for basically the base flows, sorry, for the perturbations by subtracting the total, by subtracting the base flow equation from the equation from the which govern the total flow field and the total pressure field. Okay, this is step four. Step five, what we used is we introduced the normal modes. Okay, and that's why we call it the normal mode analysis. And at last, so where do we introduce the normal mode? So we introduce the normal modes in the governing equation for the perturbations. And at step six, we substituted the form of the normal modes in the governing equations. That equation 5a, 5b, 5c, and 5d. We substituted the form of normal modes that we got, and then we eventually found out the linearized equations for perturbations in terms of the normal modes that we had. Okay, so as you can see in these equations, we have these wave numbers alpha, beta. Okay, we also have c, which is the eigenvalue, which we will eventually calculate. Okay, and then we have these wave numbers as well. Still, our problem is not solved, typically because again this so so what do you see? We see that there is this equation 6a to 6d is also a coupled set of equations. But can you tell me what essentially did change when we moved from equations 5a to d from 6a to d? What did we, I mean, we did something, okay, by introducing the normal modes. Yeah, go on.
It became from PD to OD.
Yeah, exactly. That's very nice observation. So what you saw is by introducing the normal modes, and that's the beauty of like the normal mode analysis. Okay, just like that form that we assumed in transient flows or whatever we did. It's a similar way that we did. Okay, but nevertheless, the idea was to convert the PDE. So we did one, so we solved one part of the puzzle. The idea was to convert the coupled PDE into a coupled ODE. Now a coupled ODE is solvable. Okay, so still, I mean, we cannot do this analytically, but at least numerically, a coupled ODE is an so it's solvable. Okay, you can basically solve that. But since we don't want to see numerical solutions as of now, okay, we will again do certain simplifications and certain things here. We'll use something which is known as the squares transformation, and we will see what squares transformation means. But that we will see it in the next class. But in this class, we will stop it here to this point. If you have anything to suggest or discuss, you can ask me, or we will continue from this step, that is step 6, in the next class. And then in the next class, we will draw certain insights of the infamous Rayleigh stability equation and see that we will see certain more criterias. Okay, then how to apply the Rayleigh stability equation in order to assess the stability of certain flows, and so on and so forth. Okay, so if you have any questions, you can ask, or else like we will call it a day today. Thank you for joining this session. Yeah. Do you have any questions?
Yeah. Yeah, in the next class, can you also highlight like what are the various domains or cases where we can use this in applications of this
Okay, sure,
analysis?
sure. Okay, I'll try to obviously find it out. That's a good question. So you want to see that where can we apply linear stability analysis? That what you are saying?
And applications in practical scenarios.
Okay, sure. Apply linear stability analysis. Okay, I'll try to find, and even if so we may not have time to do the math, okay, because you can see one problem is like it takes 2 class to like finish that. But I will give you certain insights on how to essentially how do these things work basically. Okay. We may not have the time to like completely analyze the problem, but I can give you certain examples where. So, for instance, you can use linear stability analysis in studying gravitational waves. Okay, so there is kind of an instability known as Kelvin-Helmholtz instability. Okay, so it's like whenever there is a flow of a fluid, flow of two layers of fluid, which basically have a relative velocity between the two fluids. Okay, so whenever there is a two fluid that are flowing and one fluid have a relative velocity with respect to the other, then you see a certain kind of instability known as Kelvin-Helmholtz instability, and the gravitational waves that you see in the ocean, okay, essentially follows that Kelvin-Helmholtz instability. And you can do linear stability analysis for Kelvin-Helmholtz instability. Okay, I will show you. So I'll not do the KH instability. It's a very big problem, but I will give you a hint how to deal with Kelvin-Helmholtz instability. Maybe in the next class. Is that okay? And of course, so there are more types of instabilities. For instance, uh, there is something which is known as capillary instability or Rayleigh-Benard instability. Did you hear the name?
Yeah, yeah. So
So
convectional thermal rules.
yeah, exactly. Yes. No, no, no. That's so capillary instability is like whenever there is a jet of water flowing, okay, you see initially the flow doesn't break down, and then after a certain length, you see the jet essentially breaks down into like subsequent drops. Okay, I would not say they are drops, they are not exactly drops, but the jet essentially breaks down. Okay, so that's not so people generally like misconceptualize it as a transition from laminar to turbulence, but it's always not the case. Okay, it's a kind of instability which is known as capillary instability. Okay, it has to do with those surface tension and like the gravity. It's an act of surface tension and gravity which basically plays the role. But yeah, this is another kind of instability known as capillary instability. But so far as my knowledge, I have not seen problems where linear stability analysis is applicable in studying capillary instability. But of course, I will have a look and let you know in the next class. But Kelvin-Helmholtz instability, of course, you can study using. You can very well like frame the framework of Kelvin-Helmholtz instability using linear stability analysis. Okay. All right. Thanks for the suggestion. I'll have a look on this. Okay. But if you have any questions on this, whatever we saw today, you can you can let me know, or you can post it in the discussion forum wherever you wish. So if not, we will call it a day here and we will end this class. Thank you for joining. We will see. We'll meet in the next week. Thank you. All right, I'm calling off the meeting.